Hi everyone, welcome back. Today we're going to talk about atmospheric moisture. This is the first part of the Chapter 6 lecture. So we're going to talk about all the different ways that moisture gets into the atmosphere and the different types of moisture that exist in the atmosphere. Here we can see clouds and fog over Taipei, Taiwan, which is two types of atmospheric moisture. So when we look at this picture, this is a picture of Perito Moreno Glacier and Lago Argentino in Patagonia, Argentina, which I got to visit, which was a lot of fun. And so when you look at this picture, we want to say, where is the water in this picture? So quite obviously the lake, there is some water, water in the glacier, but also there's a little bit of snow up there, but there's water in the atmosphere, right? We have plenty of water in our atmosphere, sometimes more water than at other times, but water exists in our atmosphere beyond what we can just visibly see. And so when we think about the total water on the planet, 97.5% of that total water is salt water, so not really accessible to us for drinking or anything else. Only 2.5% of that water is fresh water. And then of that 2.5%, only 0.4% is surface water and atmospheric moisture. And so surface water includes rivers and lakes. So just imagine the very, very small percentage of water that is in the atmosphere, but it is very, very important. And of that 0.4% of that 2.5%, only 9.5% of that is the atmosphere. You don't have to know these numbers. I'm just trying to give you an idea of how much of a small amount of water that is. So atmospheric moisture only makes up 0.0095% of the world's water, but it's extraordinarily important. So we'll talk more about the hydrologic cycle a little bit later in the semester, but basically water travels through the hydrologic cycle. We can see here we have rain falling, some of it percolates into groundwater and lakes, some of it runs off to the ocean, and then we get evaporation again, precipitation, and so this cycle that is continuing on and on and on is how we clean all of our water. It's also important to note that the water that is on this planet now is the water that has always been here. It's the same exact water, right? We're not making a bunch of new water. We're just recycling it and cleaning it. So the world's water supply is finite and constant, right? So that amount of water that exists on this planet is not changing. It's just cycling through the system. And it changes phases, and we'll talk about phase changes, and locations over time. So it can go from groundwater to the ocean, to clouds, to rain, to rivers over time. And this is how, again, we clean our water. And so when we talk about phase changes, water going to ice and ice into water is probably the biggest one that we're familiar with. But evaporation is when water goes from a liquid, right here, to a gas. Condensation is when it goes from gas to a liquid, and that can happen condensation on a cold glass of water on a hot day, or it could be in the form of precipitation and clouds and precipitation. Oops, excuse me. Let's go back. And then ice, this is not the one we're really concerned about in this lecture. We're mostly going to be talking about evaporation and condensation. Humidity is the amount of water vapor that exists in the air. There are two different ways to talk about humidity, relative and specific humidity, and I'll talk about those next. But every temperature has a water vapor capacity. That means for any given temperature, there's a certain amount of water that it is capable of holding. The maximum amount of vapor possible in the air at that temperature. And so warmer air has a much higher capacity to hold moisture than colder air does. Oops, excuse me. And so that's important to know. Colder air can hold a lot less moisture. You can't have a very, very humid, cold day. There can be a lot of moisture in the air, but warmer air can hold a lot more moisture. So two ways of talking about humidity. The first is specific humidity. and that is the actual amount of water vapor in an air parcel relative to other gases. This is not usually the way that we talk about humidity, especially if we look at the weather and we look at humidity measures for the day. That's relative humidity that I will get to next. But this is an actual measurement of how much water is in the air, and it is measured in grams per kilogram. Warm air usually has a higher specific humidity, and cold air usually has a lower one, again, because that warm air can just hold a lot more moisture than cold air can. This is not always true. If you're in a desert and it's really, really dry, it can be really, really hot and have not a lot of moisture in the air, or you could be kind of in the Pacific Northwest in the middle of a cloud, and that will have more moisture in the air. But generally speaking, warmer air usually has higher specific humidity. This lets us predict condensation and precipitation, right? When it gets to a certain point, the air will not be able to hold any more moisture, and we'll get condensation. And we'll talk about that in just a minute. Relative humidity is how we normally talk about humidity. And if you watch the weather and it says, you know, the humidity today, it's about 45% or 65% humidity, this is what they're talking about, relative humidity. Relative humidity is how much water vapor is in the air relative to water vapor capacity. And so that is dependent on temperature. A relative humidity of 70% on a warm day is going to actually have a lot more water in the air than a relative humidity of 70% on a cold day. So it's calculated by, you don't necessarily have to know this, but relative humidity is specific humidity divided by water vapor capacity. And it's expressed as a percentage. And so right now, if you were to go to weather.com, put in your location, it's going to give you a relative humidity. So example, humidity is at 75% means that the air is holding 75% of the water vapor it can possibly hold based upon its temperature. And so here we see a nice foggy day, which we tend to get less of here in San Diego. Saturated air means the air is holding 100% of the moisture that it possibly can. The air is at capacity. It cannot hold any more moisture. No evaporation is going to occur. That air cannot just take up any more moisture. And that's when condensation occurs, and you will get clouds and or fog. Precipitation may occur. It doesn't necessarily mean it's going to occur. It will often occur, but sometimes you can just get like heavy, thick fog, and that air is at its 100% relative humidity, and there is now condensed water molecules in the air. And so why does a humid day feel so much hotter than a dry one? So our body cools itself through perspiring, through sweating, and we do that because evaporation, we learned before, is a cooling process. So as our body brings that moisture to the surface, when it evaporates, that evaporation process is cooling to us. If the air is at a very high humidity, less evaporation can occur. So it's going to feel, a humid day is going to feel much hotter than a dry one. If you are in the desert and it's very, very dry, you're actually losing a lot more moisture. You're still perspiring a lot, but you don't really feel that perspiration on you because it's just evaporating so quickly. So a higher relative humidity means less evaporation is possible. And you know, if you put your laundry outside to dry on a very humid day, it's going to take a really long time, as opposed to if you put it on a very dry day, that laundry is going to dry pretty quickly. And so again, relative humidity changes as temperature changes. So as air cools, and here's a little thing showing temperature, as air cools, relative humidity gets higher. It gets closer to 100% because that cool air can hold less water. And as air cools, clouds and fog are more likely to form. So if it's a very, in the morning liable to see more clouds, more fog, the air is cool, as opposed to a hot summer afternoon where we might see less. And you can actually even, somebody controlled the temperature and relative humidity in a room as part of an art installation, was able to create a cloud indoors. So once that room reached absolute capacity, they were able to form a quick cloud. This is very, very hard to do inside, which is why we don't see clouds inside. And so again, here is a temperature map and humidity map and a pressure map of a given day. But you can look here. We have some very, very high humidity and rainfall in areas where it's very hot. So we're getting some rain, right? It's cold in San Francisco here, but it still has very, very high relative humidity because that colder air is at capacity. As opposed to out in the desert, we're having very, very low relative humidity. The air is very, very dry. It's warm, but it's only holding a small amount of what it can. The dew point, which you'll also see if you go to weather.com, is the temperature at which condensation occurs, given its current humidity. So this is based on observed specific humidity, that initial one, because the relative one is going to change based upon the temperature. 65 degrees or higher dew point feels very sticky to us. So you can have a cold day that has relatively high relative humidity, but if the dew point is low, which it normally will do, it's not going to feel very sticky to us on a cold day. And so if you think about this, when do we see dew, right? We normally see it in the morning, right? Because in the morning, the air is coldest, that dew point is going to be lower, it's going to be able to hold less moisture in the air, so we're more likely to get that condensation in the morning. I have a small child, she's only 3 years old, and sometimes we go outside in the morning and the car is wet and the ground is wet, and she says it rained, and I said, no, it's just dew, and that's a really hard concept for her to understand, that it's just condensation that's occurring because it's so cold outside. The next thing we're going to talk about is the adiabatic process, which we're going to talk about this. We talked about this a little bit before. We'll touch upon it again a little bit later. But basically, as a parcel of air rises, it expands and cools, and the pressure decreases. And so this is a parcel of air that is rising through the stationary air surrounding it. So think of it as a big pocket of air that is rising, and as it rises, it's cooling. The pressure decreases, and so the temperature then decreases, but no energy is lost, right? We talked about as you compress air before, there's no loss of energy, you get heat, but there's no gain or loss of energy. So temperature decreases, relative humidity increases, right? Because as that air gets colder, it's able to hold less moisture, so that relative humidity is increasing. And that air is going to approach a dew point. And so the big idea here is that lifting of air causes clouds to form. So as this air rises, it is cooling, it is able to hold less moisture, it's going to hit a dew point, you're going to get condensation. It's a little bit hard to see on my screen, but hopefully a little bit better on yours. And you are able to then get condensation, which is why we have, on a cloudy day, those clouds are generally speaking up pretty high. And so here, this picture was taken in Thailand, very beautiful there, but we see these flat-bottomed clouds right here, right? So you can see there's this definite point that the air has risen, it is cooled enough that it has reached capacity, and now condensation is forming. This is called the lifting condensation level. And so we can see that LCL, that lifting condensation level right there. And so this is the elevation where rising air reaches the dew point. And it's predictable based on lapse rates. So air cools at a very specific rate as it rises. So below this LCL, it cools at 5.5 degrees per 1,000 feet, which is called the dry adiabatic rate. And then above that, it cools a little less quickly. It cools 3.5 degrees per 1,000 feet above the LCL, which is called the saturated adiabatic rate. So if you know the dew point, you can actually look up and know what the temperature is at that lifting condensation level. And you can also calculate how high that is based upon these predicted lapse rates. And so that condensation, after it's condensed, it slows that cooling process down, which is why that rate changes above the LCL. And so basically what we're talking about here is lifting air. We're going to go through the 4 primary causes of lifting air, and then we will end this first part of chapter 6. And so we want to think of these geographically. Where are we likely to see lifting happen? And so the first one is convection. So here you're getting the sun heating up some air. That air is then rising because it has warmed up. Then it is cooling as it goes up, and we're getting condensation, right? So a warm air of parcels rise from the surface. It keeps rising if warmer than the surrounding air. Again, we're think of this as kind of a pocket of air. And this air kind of becomes unstable, and that instability is relative. It will rise as long as it is warmer than that surrounding air. And the air gets more stable when it is cooler than the surrounding air, and it either will sink or stay at the surface. But as that air rises, it's going to hit that dew point. You're going to potentially get clouds that forms. And so here is looking east from North Park, San Diego on a hot summer day, and you can see that lifting condensation level right there. It's a hot day. The air is rising. It's then cooling. It's hitting that dew point temperature, and you're getting those clouds that are forming. The second cause of lifting air is convergence. And so we get a low pressure area. We talked about pressure last time, but so basically when you have a low pressure area, air is going to rush in from high pressure areas and then be pushed up. So it's colliding and it is forced up in this area of convergence. It's converging on one another. And this is why we see rain in low pressure areas, right? We talked about the subpolar lows where we see rain. We talked about at the equator we see rain. This is due to convergence. So that ITCZ that we talked about last time, that's a low pressure area. That's why it always has clouds. You have converging air right there. Oh, and again, at the subpolar lows, which I just said. And this is also where we're going to get cyclonic storms, which we're going to talk about in the very near future. The third cause of lifting is fronts. And so this is when a mass of warm air encounters a mass of cold air, and you might hear on the weather or the news a warm front is coming in or a cold front. But as those two collide, the warm air kind of rushes up over the cold air because it's warmer, so it's going to rise. And there you're going to get that condensation right there. A front is just a boundary between air masses, and we're going to talk a lot more about fronts. And again, when you get a warm air that's colliding with a warm air mass that's colliding with a cold air mass, you're going to get that warm air being pushed up on top of that cold. And that air is not going to mix. Excuse me. They occur most powerfully where there is a very cold air and a very warm air are meeting, mostly at the mid-latitudes. The fourth type of lifting is orographic, and orographic is just in relation to mountains. So we get prevailing winds that blow air onto one side of a mountain As it rises up, it cools and you get rain, and then you get a rain shadow on the other side because that moisture can't make it over. So air is pushed up the side of the mountain. Clouds form above the lifting condensation level on the windward side. This is the windward side or the wet side. This is the leeward side or the dry side. And air descends on the leeward side and it warms and that water evaporates and you get these really dry conditions in areas called rain shadows.